Right, we've been given this table of the cost of various sources of energy in 2020 in pence per kilowatt hour. Okay, so we have to say for part A why France will still probably be using nuclear power in 2020. 2 marks. Well, straight off the bat, 1 mark. It's cheaper. Nuclear, 7.8 pence per kilowatt hour. However, in your exam, don't just write nuclear power is cheaper. You'll probably still get the mark, but this is an important general exam tip. Be as detailed with your answers as you can be. Don't just write it's cheaper. Say that the cost per kilowatt hour for nuclear energy is less. It's a more grown up, less lazy way of answering, and it's a tip you should follow in all your exams. Okay, 2nd mark. Why would France still be using nuclear power in 2020? Well, God, I can't think. Oh yeah, it's more reliable, of course. Solar power and wind power, unreliable. You can't always guarantee that the sun is going to be shining. You can't always guarantee it's going to be windy. You can guarantee that there's always going to be a tide, but with nuclear power, it's 100% reliable. It's always there if you need it. Anything else? No, that'll do. 2 marks. Okay, moving on. Part B. Right, yes, they wanted 2 disadvantages of nuclear power stations. Well, what's bad about nuclear? Produces loads of nuclear waste. Or radioactive waste is an even better way of putting it. And it remains radioactive for many years. So it has to be buried deep. I think they put it under, I don't know where they put it, but they put it deep underground somewhere. And that's clearly very bad. What else? It's non-renewable. In other words, there's only a limited supply of the radioactive elements that we need to provide us with nuclear energy. But solar power it's almost in infinite supply. The sun is not going to burn out. It's middle-aged, our sun. I think it's, let me get this right. I think our sun is about 6 billion years old and it's middle-aged. So it's going to be around for around another 6 billion years. It might be 5 billion or 4 billion, something like that. It's of the order of billions anyway. It's brilliant that, isn't it? The sun is going to look the same as it does now, or almost the same, for literally billions of years from now. An essentially infinite supply of energy. Anyway, I'll get off my soapbox. Tidal, yeah, that's just constant. The moon's not going anywhere. Wind, well, assuming there's no complete climate breakdown, then there's always going to be wind. Okay, it's non-renewable. What else? Yeah, it's only 2 marks this question, isn't it? Yeah, so that'll get you 2 marks. But if you have a nuclear accident, if something goes wrong at the nuclear power station, Chernobyl, for example, that's very, very bad. Okay, next. What do we have to do? Right, yeah, it's this thing. Okay, they've told us that these solar panels have an efficiency of 0.15 or 15%. The energy input to them is 3.2 kilowatts, and we have to calculate the useful power output. So we need the equation for efficiency, and efficiency is useful energy out over total energy input. Right. And we have to calculate useful power out. So, okay, I've written this as energy, but it also works with power, because power is energy per unit time. So this could be useful energy out in an hour divided by total energy in an hour. So energy and power are interchangeable here. So we want useful power out. So we want this thing on top. So we have to get that by itself, rearrange. So I'm just going to call it, let's call it P. Let's call it energy in I, and let's call that E. So we've got E is power out over energy in. Therefore, what do we want? Power out, P. Therefore, P is E times I, which is 0.15 times energy in is 3.2 kilowatts. Ordinarily, you'd have to convert this to watts, but you can leave it as kilowatts in this case because that allows us to write the power out in kilowatts. 0.15 is dimensionless, it doesn't have any units. So if we write that as 3.2, then the P will be also in kilowatts. So stick that in the calculator and you get 0.48 kilowatts. Right, finally this thing. Right, we have to suggest why manufacturing cost of these three different types of solar panel is possibly more important than the efficiency of the solar panel. One might immediately think that efficiency is the most important thing. This 20% efficient panel gives you twice as much energy as the 10% efficient panel. However, it's 8 times more expensive. And that's essentially the reason. You can argue that manufacturing cost is more important because per unit cost, you actually get more power or more efficiency from this one. I can put that a better way. It costs a lot more for the more efficient panel to get the same. Right, I've got it. I know how to explain it best. With the cheaper this is how to do it. With the cheaper panels, you can buy a lot more of them for the same price, the more efficient ones. So even though each individual panel is more efficient, there are far fewer of them, so you actually get more energy out of the cheaper ones. Yeah, that's the way to do it. Okay. However, ideally, it would be great if you could calculate, write down in another column here, the efficiency you have per unit cost. So just divide the efficiency by the cost. Okay, so that divided by that. and you get, well, 20 divided by 40, it's 0.5 for that one. 15 over 22.5 is 0.6 recurring, and 10 over 5 is 2. So you can see that the efficiency per unit cost is actually highest for the cheapest one and lowest for the most expensive. You don't need to do that in the exam, as long as you've explained it nicely, probably better than the way I did earlier. But again, that will endear you to the examiner, which is never a bad thing. Okay, I think we're done. Or should I say, I think we're finished. This isn't the USA. Dear me. Although for my American audience, we're done.